Welcome to this edition of The Explainer. I am absolutely thrilled you're here today. We are taking a literal journey of scale. We're going to start at the very edge of our expanding universe and zoom all the way down, past the solar system, past our atmosphere, right through the dirt under our feet, down to the absolute center of the Earth. So if you've ever felt kind of overwhelmed by physical geography, well, you are definitely in the right place. By the end of this explainer, you'll see exactly how all these giant puzzle pieces fit perfectly together. Here is our flight plan for this zoom-in journey. We'll be hitting the vast cosmic scale, Earth's origins and evolution, mapping the surface, deep inside our planet, and finally, earthquakes and seismic waves. Treating these facts not just as random data points, but as a spatial descent makes the whole physical world remarkably easy to grasp. Okay, let's dive into Section 1, the vast cosmic scale, from the Big Bang to the solar system. Right, so before we can understand the ground we walk on, we really have to understand the space it floats in. Our whole understanding of the cosmos basically rests on two massive concepts. First up is the Big Bang theory, which is also known as the expanding universe hypothesis. It was Edwin Hubble, back in 1920, who actually provided the crucial evidence that our universe is expanding. Then, zooming in a little closer to home, we've got the nebular hypothesis to explain how our own solar system formed. This idea was originally floated by the German philosopher Immanuel Kant and then revised by the mathematician Laplace way back in 1796. Now, when we talk about space, obviously we have to talk about distance. And I really want to clear up a super common misconception right off the bat. A light year? It's a measure of distance, not of time. Light travels at an absolutely blistering speed of 300,000 kilometers per second. So a light year simply represents how far light travels in one entire year at that speed. It totally anchors the massive, massive scale of the universe. To put a hard number on it, 1 light year equals 9.461 times 10 to the 12th power kilometers. I mean, that is a mind-boggling number. To give you some perspective on just how vast that is, think about our sun. The average distance between the sun and the Earth is roughly 149.5 million kilometers. In terms of light speed, that means we are just 8.311 light minutes away from the sun. The universe is just unbelievably huge. Which brings us to Section 2, Earth's origins and evolution, from barren rock to life. Let's leave the vastness of the solar system behind and zoom right in on our newly formed early planet. But before we look at how it evolved, I want you to ask yourself a question. Exactly how old is the Earth? Just think about it for a second. Well, here's the answer. 4.6 billion years. That is the massive chronological stage upon which our planet's entire evolution takes place. So let's see how that actually played out over all that time. Following this timeline reveals a really incredible narrative of growing up. 4.6 billion years ago, Earth definitely wasn't the beautiful blue and green marble we know today. It started out as this barren, rocky, intensely hot object, wrapped in just a super thin atmosphere of hydrogen and helium. It was incredibly hostile. But then, fast forward to about 3,800 million years ago, and life finally begins to evolve. And honestly, the most transformative step? Sometime between 2,500 and 3,000 million years ago, the process of photosynthesis evolved. That literally changed the trajectory of our planet, turning it into the life-supporting ecosystem we have today. Let's move to and see how this builds in Section 3, mapping the surface, understanding our ground. We've gone from the edge of the universe to the formation of the Earth. Now let's zoom right down onto the very surface of our world to see how humans actively study it. So the term geography itself was actually coined by a Greek scholar named Eratosthenes way back between 276 and 194 BC. But as the field grew, two major approaches emerged in the 19th century, championed by two German contemporaries. On the one hand, we have systematic geography, introduced by Alexander von Humboldt. This is more of a general, overarching approach. On the other hand, Carl Ritter developed regional geography, which takes a much more specific regional lens to study the Earth. And what exactly are we studying on that surface? Well, the fertile ground itself. Soils form through a process called pedogenesis, and this depends on a few things: parent rocks, climate, biological activity, and time. Actually, time is the real secret ingredient here. It's what provides maturity to soils and develops those distinct soil profiles. Meanwhile, the exact mix of temperature and precipitation dictates the density of our forests and the quality of our grasslands. Now, here is a truly wild fact about the surface we walk on. Gravity is not uniform. The gravitational force, or G, actually changes depending on your latitude. It's stronger near the poles and weaker at the equator. Why? Well, because the Earth bulges in the middle, the distance from the center of the Earth to the equator is actually greater than it is at the poles, and the further you are from the center, the less gravity you experience. So you technically weigh a tiny bit less at the equator. But latitude isn't the only thing messing with gravity. Readings also change based on the mass of the material hiding right beneath our feet. The uneven distribution of mass inside the crust influences gravity, making the readings differ from what we'd mathematically expect. We call this difference a gravity anomaly, and these anomalies are super useful. They act almost like a geological X-ray, hinting at the hidden, uneven mass buried under the dirt. All right, Section 4, deep inside our planet. Journey to the core. It's time to dig past that surface, right through the crust, and journey downward into the deep unknown. Just to understand what we're dealing with, Earth's radius is 6,370 kilometers. That is an absolutely incredible distance we'd have to travel just to reach the center of our planet. Now, what's really interesting about this descent is the structure. Going down, we hit distinct layers: the crust, the mantle, the outer core, and the inner core. But it's not just the materials that change. As you go deeper, temperature and pressure aggressively increase. And on top of that, the actual density of the material goes up too. So the deeper you go, the hotter, the heavier, and the more pressurized the whole shebang gets. Which brings us to Section 5, Earthquakes and Seismic Waves, the Restless Interior. Now you might be wondering, if no human has ever dug anywhere close to the mantle, how do we actually know about all these deep layers? Well, the answer lies in the violent energy of our restless interior, earthquakes. All natural earthquakes happen in the lithosphere. But to understand them, we have to clear up two terms people mix up all the time. The actual point deep underground where the energy is released, that's the focus, or the hypocenter. The epicenter, on the other hand, is the point on the surface directly above it. Because it's right on top of the action, the epicenter is the very first place to feel the earthquake waves. And how do we catch these waves? With an instrument called a seismograph. These record the waves as they hit the surface. But here is the ultimate key to unlocking the inside of the Earth. The velocity of these earthquake waves actually changes as they travel through materials of different densities. Denser material means higher velocity. Plus, their direction shifts as they reflect and refract off those different densities. We're mainly looking at two types of body waves here. First, we have P waves, or primary waves. These are fast, they arrive first, and they act a lot like sound waves. Crucially, P waves can travel through gas, liquid, and solid materials. Then we have S waves, or secondary waves. These show up with a bit of a time lag. But here is the most important structural clue you need to remember for sure. S waves can only travel through solid materials. So I want to leave you with this final provocative thought. If S waves can strictly only travel through solid rock, what does it tell us when our seismographs show those exact waves suddenly stopping dead in their tracks deep underground? It tells us exactly where the solid rock ends and a liquid layer begins. Just by listening to the echoes of violent earthquakes, we can effectively see the liquid layers of our restless planet without ever having to dig a single hole. And that is the true power of physical geography. Thank you so much for joining me on this explainer, and keep looking deeper.